section 4.1 through 4.3. We'll start with 4.1. Chapter 4 is actually, you're going to find that it's we're going to rethink about a lot of things that we've actually thought about before, using sometimes a little bit different words and some bigger overarching ideas. But a lot of the times it's going to come down to doing the same things and the same words and the same notions that we've talked about before. That is a linear independence, linear dependence, a spanning set, and a change of basis or basis and coordinate systems. So all of these things we're going to think about, but coming at it from a slightly different, bigger picture angle, and that's what we start talking about in chapter 4.1, which is this idea of what we call a vector space. So a vector space. So far we've thought about vectors, and vectors for us have been simply lists of numbers, right? So something in R6 or R10 or R2 or R3, that's a vector. But we're going to take a step back and abstract it just a little bit for now, and I'm going to give a formal definition, and we'll look at a bunch of examples of what I mean by a vector space. Definition: a vector space is a set V, so it's just a set of objects. So for Rn, that's the lists of numbers. It's a set V with two operations, which we'll call addition and scaling. So addition plus and scaling we'll call dot times for now, and we'll see how that works, such that a whole bunch of things are true. One, if V1 and V2, we're going to still write them as vectors as before, with this same notation. So if V1 and V2 are in the set V, then so is V1 plus V2, but also scaled any way we like. So C1 V1 plus C2 V2 for any C1 and C2 in R. So we're going to be able to scale by any real number and still stay in the set, and we're going to be able to add up vectors that were in the set and stay in the set. So remember from our language from before, that's the same thing as saying that it's closed under addition and closed under scalar multiplication. So we start with two things in the set, we add them up, it's just something else that's in the set. We scale, we start with something in the set, we scale it, it's still in the set. Okay. Okay, and so we're going to have a couple of other technical requirements as well. Actually, a bunch of them. I'm going to write them down once, but then most of the time we'll just be able to ignore these requirements. Two, so there is a vector 0 in V for which V plus 0 is 0 plus V is V for all V. Right, so there's just a special 0 vector. And again, we're going to look at a bunch of more examples of different vector spaces other than just Rn and see how these things all apply. 3, U plus V is V plus U. So I can add in either order and I get the same thing. 4, we can associate, so this is an associative rule. U plus V plus W is U plus V plus W. 5, we can associate with scaling. C2 times the vector V then times C1 is the same thing as C1, C2 times the vector V. So everything that we expect to happen has got to happen. So there's no tricks here, right? So 6c times u plus v is cu plus cv. So we can distribute a scale. This is a scalar. We can distribute it to a vector just as if we want. Notice that we never talk about u times v for two vectors. We can't multiply vectors. For two vectors in Rn, we never multiply them. We dot them sometimes when we get a real number back, but that's not a multiplication of vectors because it doesn't return another vector. There is a cross product only in R3, but it doesn't work in general vectors. So we don't really have a multiplication. Also, so 0 times any vector v is the 0 vector. And finally, 1 times any vector v is just the vector v. So, lots of technical things which just say that everything works the way that we want it to work. The algebra of vectors has to work the way we want it to work. In general, we're going to think about a vector space as a set where we can add stuff up and scale it as well. So let's look at some examples of those things. And we'll start with the one that we already know. So if v is just Rn. So if v is Rn, we can add vectors together in Rn. We already know. We get another vector in Rn. We can scale them. We get another vector in Rn. Here's another one. All right, so this is a different notation. This is a script P, or a block P, and we're going to call this P sub n. And what this is all nth degree polynomials. Right, if I have two 10th degree polynomials and I add them up, I get another 10th degree polynomial. So I can add two polynomials together and it stays and the degree doesn't change. If I take a 10th degree polynomial and I scale it by any constant, I multiply by 6 or -4 or 32, the degree of the polynomial doesn't change. So by adding, I stay within all specific degree polynomial, and by scaling, I also stay within all specific degree polynomials. So these polynomials are in fact a vector space. I can look at all infinite sequences of real numbers. Right, so for example, a small vector in this case might be, here's an infinite sequence of real numbers. But it goes on forever. Right? But I could add up two of those things. If I had two different infinite sequences of real numbers, there's a pretty obvious addition. Just add up piece by piece, component by component. And I can also scale the whole thing, and I get an infinite sequence of real numbers. So we have a set, we have an addition, and we have a scaling. And those things together make for a vector space. I can look at the set of all 3 by 3 matrices, and in fact it doesn't have to be 3. I could say 6 by 6 or 10 by 10 as long as I had square matrices. We can add them up, right? So addition works just like we'd like it to, and we can scale. So both of those things work. And all of those algebra properties are also satisfied. Okay, subspaces. A subspace. We've already actually seen this word before in our understanding of Rn. We're going to look at it again a little bit abstractly now. We've taken a step back to think about a vector space as an abstract object, which could take on a lot of different meanings. And we're going to look at all of these ideas in general, and then remind ourselves how they worked in the Rn case as well. Remember, a subspace is really just a subset, which is also a vector space. That's a little different than we described it before, but that's really all that we need to think about it as a subspace. So a subspace of a vector space is just a subset where it's still closed under addition and it's still closed under scaling. That's what it means to be a subspace. Right, so closed under addition, scaling. And remember that closed means if I add two vectors up, it stays in the set. If I scale a vector, it stays in the set. Okay, so in R3, that's one of our favorite, is the xy plane a subspace? Well, the answer is yes. Because if I have R3, and I take two vectors that stay on the xy plane, and I add them up, it stays on the xy plane. And if I take a vector that's on the xy plane and I scale it, it stays on the xy plane. And that's really all that it takes in order to be a subspace. Closed under addition and closed under scaling. So is the unit circle in R2 a subspace? So here's R2, the xy plane. The unit circle is the circle here. If I looked at all vectors which stayed on the unit circle, does this form a subspace? Well, no. Because if I add up any two vectors that are on the unit circle, it goes off of the unit circle. So no. It's not, or I could scale any of these vectors and it's no longer on the unit circle. It actually doesn't satisfy either of those. So it's not closed under addition or scaling. Let's say that V is P4. All fourth degree all fourth degree polynomials. Fourth degree polynomials. Let's say we have our question is H equal all polynomials with positive coefficients? Is that a subspace? Well, it is closed under addition, because if I take two fourth degree polynomials and add them up, if both of those polynomials have positive coefficients, then after I add them up, they still have positive coefficients. So it is closed under addition. And be careful, because it at first glance feels like it's closed under scaling as well. If I take a fourth degree polynomial with positive coefficients and I multiply by 6, well, then it still has positive coefficients. But be careful, because it has to be closed under scaling by any real number. Right, so it's not closed under scaling by negative numbers. If I take a fourth degree polynomial and I multiply by -6, well, if the original one had positive coefficients, the new one does not. So it has to be closed under any scaling, positive or negative, and also under any addition. So this is no. Here's another example of a subspace. So suppose that we started with R4 and we looked at, and let's let H be the span of a couple of vectors. Remember, a span is all linear combinations. That's what a span is. That's the definition of a span of some vectors. All linear combinations of the vectors. But that's by definition made to be a subspace, because if I have a linear combination of this, well, that's just a scaling times this and a scaling times this, and I add it up, well, then I still have a linear combination of those things. I've just changed the scaling factor. So really, span is created to be a subspace. And if I have the span of any set of vectors, then I will get a subspace of the original vector space. All right, that's what we got for 4.1. Next, we'll move into 4.2. We're interested in some specific subspaces, and really in this case, as they just apply to vectors in Rn. So we're going to be looking at the column space. We've already seen these things. The null space and linear transformations. And so this really will just not be very much different from section 2.8 that we've actually spent some time thinking about. But so remember from last time, if I have any set of vectors, the span of those vectors, v1, v2, vn, is always a subspace. Because when we take linear combinations, and you add two linear combinations up, you get another linear combination. If you scale a linear combination of vectors, you get another linear combination of those same vectors. So span is set up to be a subspace. Okay, so remember that if I have a matrix A, the column space of A is the span of its column vectors. And just because of this fact, because the span of anything is a subspace, the column space of A is a subspace. Now let's be careful about what it's a subspace of. Suppose we have this matrix. If this is our matrix, then column A is the span of the column vectors. And if I'm looking at the span of these column vectors, well, it's a span of vectors that are in R4. This is a subspace of R4. Now remember, it's a different question as to whether or not we actually need all three of these vectors. It's possible that we could write column of A as just two of the vectors, or even just one, depending on how these are related. That's a different question that we'll come back to later. Which of those vectors do we actually need? It's related to the question of linear independence of the vectors as well as some other things as well. We've also seen the set null A, which is the set of all vectors with AV being 0, null for 0. So null A is all vectors which get sent to 0 under matrix multiplication. But notice that this is in fact a subspace. Right? It's a subspace because if I take two vectors which are in the set, so if V1 and V2 are in null A, then A V1 plus V2 is A V1 plus A V2, which is 0 plus 0, which is 0. So if I have two vectors that are in the null space, when I add them up, it's still in the null space. And also if I have a vector which is in the null space and I scale it, then I get C times AV, which is C times 0, which is 0. So by scaling a vector which is in the null space, I still get a vector which is in the null space as well. So in fact, null A is a subspace. But what's it a subspace of? Again, let's be careful about that. A subspace of R what? So we've done this before. Let's remind ourselves of how this works. Let's find a description of null A. And you'll see exactly what I mean by that. Remember, what we're looking for is we're looking for AX equals 0. That's what null A means, AX equals 0. So we're looking for a row reduction. So I'm just going to row reduce this matrix. And see what we get. So this is what we get after row reducing the matrix. Let's remember the next step. We're going to turn this into, we're looking at the solution set to this, to AX equals 0. We're going to write it in parametric form. Okay, so this becomes x1, x2, x3. So this reads x1 plus x3 is 0, x2 minus x3 is 0, and x3 is free. Which becomes x1 is negative x3, x2 is x3, x3 is free. Remember that we take every free variable and write it as x3 is some parameter. So really we get x1 is negative t, x2 is t, x3 is t. So the vector x that we started with, x1, x2, x3, is negative t, 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 which is t times negative 1, 1, 1. So the null space of that matrix A that we started with is this. All vectors that look like this one. Well, this is exactly the span of this vector. So null A is span of just this one vector. Finally, we're going to define a linear transformation in this more abstract setting of a vector space, but it's really not different than before. A linear transformation from vector space V. We can actually go from two different vector spaces between two of them, V1 to V2, which are vector spaces, is a function t from V1 to V2 between the two sets with t of C1 V1 plus C2 V2 equal C1 T V1 plus C2 T V2. So in other words, you can factor a scaling out of the transformation, and you can also distribute the transformation across the two pieces. So adding up and then applying the transformation is the same as applying the transformation and then adding. Scaling and then applying the transformation is the same as applying the transformation and then scaling. That's what it means. That's what it meant to be a linear transformation before. It means the same thing now, because in a generic vector space, we still have addition and scaling, just as before. Okay, so let's just end this section by recalling a few basic facts about the column space of A and about the null space of A. So the column space of A is the span of the column vectors of A. And so if A is, let's say A is M by N, rows by columns, then this is a subspace. So if I have M rows down, that means each column vector is in Rm. So the span of the columns is a subspace of Rm. All right, so what's the biggest this could possibly be? If it's a subspace of Rm, the biggest it could possibly be is all of Rm. Right, so this is it is equal to col A equals Rm. That's the biggest it possibly could be, if and only if the vectors that we get, the column vectors, well, let's say if and only if the transformation T, right, so x goes to AX, this has got to be onto. So I have to get everything back. Another way of saying that same thing is to say that AX equals B always has a solution. Okay, and null A, what we're actually figuring out is the solution set to AX equals 0, which we get by writing that solution set in parametric form. And so write in parametric form, and we pull off the vectors to form a spanning set. All right, null A, if A is M by N, well then, in order to be in null A, I need to be a vector that I can multiply by A by, so the vector has to match the number of columns, and the number of columns is N, so null A is a subspace of Rn. So just some differences between the two. And we'll come back and add some more when we get into some later sections. And finally today we're going to look at 4.3, linearly independent sets and bases. Again, we've seen both of these ideas before, so we're going through it a little bit quickly and just adding to it where we need to when we're thinking about the abstract vector space and reminding ourselves of how it works when we're talking about vectors in Rn. So remember linearly independence. So V1 through Vn are linearly independent if and only if. The only way to add them up and get 0 is if all of the scaling factors are 0. That's what it means to be linearly independent. There's no way to combine these to get 0 except for to scale them all down to 0. Okay. And so what that actually means for us, as far as what we're interested in this section, let's remember that how do we get a basis for what a basis is and how we get a basis for Rn, for the null space of a matrix and the column space of a matrix. Okay, so remember also that, so this is our first thing from before, also a basis is a linearly independent spanning set. So we may have a spanning set that is something that we start with and we're allowed to combine together however we want, but it's not a basis because it's not linearly independent. So let's combine these two notions together. So let's find a basis for col A, the column space of A, where A is this matrix. Well, remember that col A is the span of the vectors. So if these vectors were linearly independent, then it would be a linearly independent spanning set, which would be a basis. But if the vectors are not linearly independent, then it's in fact not a basis, and we don't need them all. So let's see what happens. How do we figure out if vectors are linearly independent? Right, so our question is, are the column vectors linearly independent? Well, the way we do that is the same way that we do anything, which is row reduce. Now remember that this one is one where our calculators get a little bit tricky because it can't row reduce something which has more rows than it does columns, so we have to add that extra column of zeros just in order to be able to row reduce. But if we do that, this is what we get. Remember that vectors are linearly independent if I get as many pivots as possible. If I get a pivot in every possible column. So, and that's not true here. I do not have a pivot. So there's no pivot in column 3. So the answer to that question is no. Right? I would need, there's not a pivot in every column. Since we don't have a pivot in column 3, that means that we actually don't need the original column 3 in order to span the same thing. So what that tells us is that the column space of A is in fact just the span of the first two columns. And we don't need them all because the third one can be created as a linear combination of the first two. So notice what we do. We take the matrix A, we row reduce it, we find out where the pivots are, we take the columns off the original matrix A, which corresponded to the pivot columns. And those form a basis for the column space of A. Right, so, and these two things here are a basis for col A. Now, as far as the null space goes, well, we've already done everything we need to do. The null space we get, remember, by finding the parametric vector form of the solution set to AX equals 0 and pulling off the vectors that we get corresponding to each parameter. Those things already are going to be linearly independent. Let's find a basis for null A where A is this matrix. Which we still get by row reducing, but remember really what we're doing, we're row reducing, we're thinking about AX equals 0, that's the null space, so we really are row reducing this matrix with an extra column of zeros. However, when you put an extra column of zeros and row reduce, that last column of zeros always stays as zeros. So we really can just row reduce this matrix and add a column of zeros at the end. So 4 by 4. And this is what we get. So that's what we get when we row reduce it. And again, we're thinking about this as AX equals 0. So we're thinking about this as a column of constants at the end. And this is what we get. So now we need to change that over to a parametric vector form of the solution. And in order to do so, we read this as x1 plus x3 plus 3x4 is 0. x2 minus x3 minus x4 is 0. x3 is free, so let's call that t. x4 is free, so let's call that s. So this becomes x1, if I bring these things over, that's negative x3, which is negative t, minus 3s. x2 becomes t plus s, x3 is t, and x4 is s. Which means my solution is the vector x, x1, x2, x3, x4, which is negative t minus 3s, t plus s, t, s, which then we break up into each parameter. So we take a vector for the parameter t, and if we do that, what we have is negative 1, 1, 1, 0. And then we take a vector for the parameter s, which is negative 3, 1, 0, 1. Which means that a basis for the null space is the vectors that we get back in the end. Okay. So let's just look at one last example of the idea of basis in a more abstract vector space. So we'll look at one last example with a more abstract vector space V, which is P3, which is degree 3 polynomials. And I should be a little bit more precise. When I say degree 3 polynomials, what I actually mean is polynomials with at most degree 3. So this is third degree or less. That actually wouldn't be a vector space if I didn't include the or less, because if I looked at, for example, x cubed plus x squared, and then I subtracted, this is one vector, and I subtracted x cubed, which is another vector. Well, I need to stay in the set, remember. I need to have closed under addition and scaling. Scaling makes for subtraction, but this would actually just give me x squared. So when I say P3, I mean polynomials up to degree 3. So let's find a basis. For P3. My claim is that a basis is just these as simple as possible polynomials. Because any degree 3 polynomial is a linear combination of these. Right, so if I had a 2x cubed minus x squared plus 4, well, this corresponds to the linear combination scaling this by 2, scaling this by -1, scaling this by 0, and scaling this by 4. These things are linearly independent because there's no way to take any of these and add them up and scale and get to anything else. These are separated by so much space. I can't turn x cubed into anything else by just addition and scaling. So this is our standard basis for P3. We have a similar analogous standard basis for any other Pn. All right, and that's what we've got for section 4.3, and I'll see you next time.